Good morning. Here we are. This is the sixth lesson of algorithmic design, and at the beginning of this lesson, I would like to answer some questions you asked me after the fifth lesson. So, and then we will focus on the implementation of the binary heap data structure that we saw on the fifth lesson too. So let me first of all answer some of your questions. The first one is why does the procedure insert value first add a node whose key is largest in the total order and then it decreases the key to the value to be inserted? So let me go to the slides. Here we are. And let me recall the procedure required to insert a new node into a binary heap. Well, insert a new value into the binary heap. So first of all, we need to insert a new node. And since we have to preserve two things. First of all, the topology, overall topology of the binary tree. And I recall you that a binary heap is an almost complete binary tree, meaning that all the levels but the last one are complete, such in this case and this case. Okay, so the only possible choice to insert a new node, of course, is to insert the new node, the node which will contain the new value we want to insert into the binary heap. I was saying the only possible choice to insert this new node is to insert it at the very last level. Okay, and since we are also requiring that all the leaves at the very last level should be pushed to the left, the only possible choice is the leftmost available position in the last level. So of course, if you are dealing with a complete tree, the only choice is to add a new level and basically attaching the new node as left child of the leftmost leaf in the last level. So let's see. In these two cases, move wrong tab. Okay. So in these two cases, I'm forced to add these two nodes. Okay. And now, since I must preserve also the heap property, I need to choose a value for that nodes which preserve the heap property. Now we have one possible choice, which is the one we saw during the last lesson, and the choice is the largest value in the total order we are using to organize the heap. So in the case of min heap, the largest number is of course infinity. In the case of the max heap, the total order we are using is greater than or equal to. So the largest number is in a kind of weird way minus infinity. And by doing so, we are basically able to add to any heap a new node. And this new node preserve, by doing so, we are guaranteed that this new node preserve the heap property. Okay, so right now we have a new heap different from the one we started with, and this new heap has one more node. Okay, now once we have done this step, of course, at the beginning we were wondering how to add a new value inside the heap. So our goal was to insert a new node and assign to the key of this node, so assign to this new node, a value, a specified value. So how can we use this step to insert a new value? Well, of course, we already saw how to decrease a key inside our heap. We saw it in the previous section, let's say, of the slides, and we can exploit that procedure to decrease the maximum value we inserted here into the value we want to insert. So, for instance, if at the beginning of the computation we were dealing with the blue part of the heap and we want to insert the number 3, by decreasing infinity to 3, we end up with this mean heap. Okay, and going here, if at the beginning computation we were dealing with the binary heap denoted by the blue nodes, and we want to insert the value 7, for instance, and please notice that the value 7 has been already inserted here. So by using the decrease keys procedure, we are able to end up with this heap. Okay, so the decrease key procedure does not change the topology of the binary heap. So that topology is preserved. Simply decrease a key and fix the binary heap property on the resulting tree. And this is what I want to tell you about this question. Okay, so no, this is not all. So what's the cost of performing this operation? Well, of course, the cost of inserting a new node is well, if you are using the array-based representation of your heap, of course, cost theta of 1, because you have simply to add an element at the end of the considered part of the array. Okay, but I mean, this cost can be also obtained by implementing in a smart way trees. And of course, the cost of decreasing the key is logarithmic in the height of the tree itself. So the overall cost of inserting a new value is big O of log n, where n is the number of elements already present inside the heap. Okay, this is it. Now let's move to the next question. So the second question was, during the evaluation of the cost of build heap, you said the height of binary heap is ceiling of log base 2 of n, but it should be floor of log 2 of n. Okay, this is not really a question, but it is correct. So let me again go to the slides and build heap. Here we are. Okay. Oh, already fixed all the slides. However, in these slides you may have seen that the height of the tree is ceiling of log n base 2, and was wrong. But actually, my motivation, my excuse to is writing the height of the tree is that it's not really relevant, and so to prove that it is not really relevant, let me go back to the whiteboard. This is the whiteboard with all the calculus we made to compute the complexity of building heap. I recall you that build heap basically keep calling heapify level by level on almost complete binary tree, and this is enough to build to satisfy the heap property. So this is the whiteboard we wrote in trying to figure out what's the complexity of build heap. And as you can see here, I sum up everything to what I thought was the height of the tree, which is wrong. So let me fix it up. So this should be floor, this should be floor, this should be floor, and let me go to the next page. Okay, this is the next page. Okay, at some point I end up with this stuff. Well, the point of this stuff is due to the fact that I was over approximating, let's say, this sum by using infinity. So let me add one further step just to our computation to see what's the point. And how can I do it? Let me delete this stuff, and let me just rewrite the previous terms as I over approximated it. So this is C times n multiplied by h0, from h0 up to, and this is h. So up to what? So in the previous whiteboard, this is it. We had the height of the tree. Now I am over approximating it by using infinity. Okay, and this was enough to end up with the computation we saw the last time. So this is and 1/2 1 minus 1/2 square, which of course is equal to, this is it. Okay, so as you can see here, despite the fact the height of the tree was wrong, and basically I was over approximating it, the computation doesn't change. Okay, so the calculus for the complexity doesn't change, because I was always over approximating the number of steps required to perform binary build heap. And this is why here we are having a big O and not a theta. Okay, and this is the answer. So it's not, basically it's not relevant. One more level on the height of the binary heap is not relevant from the point of view of the build heap, and that's why I didn't fix the problem online. So let me move to the next question. Let me see if we have any comments. Select the binary heap and nearly complete tree. Second last one, certain new leaf. Binary must leaves on the left, as on the right, isn't it? Let me just answer online a question on the slide about the heap. Binary heaps are nearly complete binary tree, so you are complete at second last level. All levels are on the last level are on the left, but right now when inserting a new leaf I saw also binary heaps with much leaves on the left as on the right, isn't it so? no. All the levels. Sorry. So someone of you is wondering, is wondering what's going on here, and or better, is wondering what's the definition of binary heap from the topological point of view. So from the topological point of view, the tree is almost complete. Okay, so up to the second last level, the tree is complete. So all the leaves up to the second last level, all the nodes in the level, all the nodes, we have all the 2 at the power of I nodes at the second last level, where I is the 8 of the second last level. Okay, and as the last level concern, we have that all the leaves, of course, in the last level we are having only leaves, and let me go back here. Okay, here. So as I said, from the topological point of view, the binary heaps are complete trees, and so up to the second last level, all the nodes are present. As far as the last level concerns, we have only leaves, of course, because this is the last level, so no more level after that one, and all the leaves are on the left side of the tree. This is it. So some of you is asking why here, for instance, in the max heap version, we are having a leaf here. Sorry, a leaf here and a leaf here. So the number of leaves on the right is equal to the number of leaves on the left. Well, this is true for this specific instance of a binary heap, but actually this is not belonging to the last level. So this node, the rightmost node, belongs to the second last level, and the last level is only filled with 4. So as far as all the nodes but this node whose key is 4, the tree is complete. And as far as the last level concerns, the only nodes we are having is the node containing 4, and this is on the left. Okay, this is it. Okay, so let's move to the next question then. And move to the next question. Okay. So about the homework, have they a deadline? Should I hand over them by paper, on Git, or what? Well, yes, they have a deadline, and the deadline is before the begin of the session you want to have the exam. So if you want to have the exam during summer session, you have to hand them before the end of May. If you want to have them on fall, the deadline is August. If you, let's say, in the worst case, you target winter, I don't suggest you to wait for the next winter, but if this is your target, I need to have your homework before Christmas. Okay, and as far as the best way to hand over your homework is to send me a link with a containing a link to a repository which contains both the answer to the questions and the code. Okay, and the code should be easy compilable and executable. And this is it. Okay, so concerning this question, I noticed that I missed to report the exam dates. So of course, due to the situation, it's not that easy to figure out a possible date for the exams, because of course I don't know even if the exams would be written or an oral exams, due to the fact that it's not possible to have a written exam, of course, online. So I mean, I have a kind of schedule, but and I really hope we can maintain it. But this is just for completeness. So let me show you. The possible schedule. Let me do it in a while. Okay, this is it, and okay. So this is the possible schedule for the written exam. I added them to. I added a slide in the very first pack of slides. So in the introductory slides, and as you can see, we have you will have 7 possible choices to have the exams spread through these academic years. So the next, well, actually half in this academic years and half in the next academic years. So from June up to February 2021, you can, from June 2020 and of course February 2021, you may have the exam whenever you want. Okay, this is it. And of course registration is mandatory, so you have to register on S3, and this should be enough to have the exam actually. So this is it. And the very last question I had was about the Strassen algorithm, the coding the Strassen algorithm. And so let me go through it. So the question was, why by extending the base case in the code of Strassen's algorithm did we improve the performance of the implementation also for instances greater than 128? So I recall you, the Strassen algorithm was the algorithm to multiply two matrices, and we implemented it in C, and so let me go to the implementation. This is the implementation we did. Okay, this is the implementation we did. And okay, so if you remember, the implementation was recursive. What's going on here? So if you remember, the implementation was recursive, and we have this if condition. Let me see if you can see it. Yes, this if condition was meant to discriminate between base cases and recursive steps. So at the very beginning, a very initial implementation, we had something like this. So if the size of the matrices we are dealing with is 1, then call the naive version of the algorithm on these instances. Okay, but then we discovered this kind of implementation was much worse than the naive version, at least on the size instances we on the instances we were dealing with. So we decided to try to change the base case, and we observed that by changing the base cases, by extending base cases in this way, we end up in a much faster algorithm. So someone was wondering why this change affect the computation also for cases which are much larger than 2128. Well, first of all, I must observe that for any case in which the size is smaller or equal to 128, we end up in performing the naive algorithm. So of course we cannot have improvement, let's say, in these cases. Okay, so let me try to show you why. So let me draw a kind of recursion tree. So this is the first call. Okay, first call of our Strassen algorithm implementation, and this is the tree of the recursive calls. Okay, now at the very beginning of our implementation, we decided to keep performing the recursion up to size 1. So this is call for instances. What? Let me rewrite it. Instances having size 1. Okay, and we noticed that this let me change it. Okay, let me move my face. I will move it. Oh, what's a mess. Yeah. So as I was saying, so at the very beginning we decided to keep repeating recursive call up to instances having size 5. So the 8 of the tree is basically the logarithmic base 2 of the initial size of our matrices, and by changing the code, we end up in, well, let me redraw it because this is a straight line, to cut this part of the tree. Okay, and why we decided to do it? Well, this is size 128. And why we decided to do it? Because each recursive call requires to allocate space for 17 different matrices. And this cost, together with the cost of the recursive call, is a constant call. It's a constant cost. So it's not dependent on the size of the matrix we are dealing with. Okay. Well, of course, it's dependent on the size of the matrix, the space we need to allocate, but the fact that we need to allocate these 17 different matrices, and the fact that we need to perform 7 recursive call, this is independent from the size of the matrices themselves. So it could be the case that it's not for sure. For instances smaller than 128, our implementation is not really efficient, let's say. So there's no advantages in using the Strassen algorithm with respect to performing the naive algorithm due to the fact that there is the overhead of allocating 17 matrices and to call 7 recursive calls. So because of that, we decided to cut that part of the tree. Okay, so the contribution in terms of execution time due to that part of the tree was removed, and that's why this effect also has effect on the matrices whose size is greater than 128. So the 8 of the tree, the number of nodes in this tree basically tells you the cost of executing this algorithm. So if we are able to cut a part of the tree, we decrease the number of nodes and we decrease the execution time and the complexity, of course. Okay. And this is the answer, I think. So I think it's more or less clear what's going on here. I think so. So these are all the questions I received so far. So we can finally move to our code, and let me go to the code then. So the goal of this lesson, let's say, is to implement the binary heap we saw during the previous lesson, so lesson number 5. And to do so, I released a repository on GitHub. The repository contains all the code you need to start the implementation and to test it. As done for the Strassen algorithm, I don't want you to waste your time in developing auxiliary function, thinking how to do the things, and so on and so forward. So I decided to go through in this way, and the name of the repository is let me see. The name of the repository is Bin Heap. Okay, so you can find it, let me see, if you go to https://github.org and Alberto Casagrande, you will find all my not github.org but github.com, sorry. Okay, you will find all my repository. Let me see where I am. Here, yeah, no, I lost. Okay, so this is the root to my repository, and the repository you are interested in is the one called ad bin heaps. So ad bin heaps. Okay. So by cloning it, you can clone it by writing git clone and so on. You end up with all you need to start the implementation of binary heaps. And as already done for Strassen algorithm, you will have a CMake. Let me see. Can I ask again a question on the homework? Yes, of course you can. Just let me know, even during this lesson. So so once you have clone the repository, you end up with all the stuff you can see here. And as done for the Strassen algorithm implementation, you need to create a make file, and you can do it by calling cmake lists, and this is enough to build a make file, to produce a make file. And by make you end up in compiling all the stuffs, and at the very beginning you will end up with two executable, which will be called which are called test delete min and test insert min. And of course, since at the very beginning we are missing the binary heap implementation, if I try to call them, I end up with something weird. So by calling test insert, which is a tool for try to insert element and delete element from a max heap and a min heap. And for instance, let's try to insert a number 3, and the computation and immediately, because we are missing the implementation of heaps. Okay, and so again, if I try to call delete min, test delete min, I end up with something similar to what we saw on the Strassen algorithms. And basically this is a test for building the data structure and removing the minimum, and we are comparing the execution time in removing the minimum from an array, so moving the minimum at the end of the array, and on an heap. Okay, of course, to remove the minimum from an array, I first of all need to find it, and this will cost scanning all the elements in the array, while on the heap it's much easier, because as you know, the minimum on a min heap is of course on the root. So so if you have a look to the table we are seeing here, you may notice that the heap column, so the time required to extract the minimum on a binary heap is always almost 0, and this is due to the fact that we are still missing the implementation of binary heap. Okay, so this is an almost complete tool. We are missing the implementation of the binary heap. Okay, now since binary heap is a really important data structure, and we will see how to use it also in different projects during the remaining part of the course. I decided to use this example to build up a library for binary trees. Okay, and this library should be as general as it is possible, and this is done basically automatically on the repository. So if you have a look to the directory, you end up in the main directory of the repository, you end up in notice that after compilation we will have something called lib being heap.so, which is basically the library for the binary heap. Okay, so of course at the moment we are missing the code, but still we have a framework to build the library. Okay, let me go to the chat. I saw that there are some questions, so just to be sure, are we the PDF of the homework on description of the last video? I think so. So someone is asking, is it possible to have the PDF of the homework on the description of the last video? It should be already there. If it is not the case, please let me know. However, you can also download the homework of the last lesson from Moodle. Okay, so by looking at the description of the video and by looking on Moodle, you should have all the slides, all the homework I've given you up to now. Okay. We have also to generalize algorithm 2, right? Yes, this is written on the so someone is asking if you are required to generalize the Strassen algorithm, meaning if you are required to generalize the API of the code we wrote to deal also with non-square matrices, and this is the case, yes, but you can find the point on the homework I gave you. And in the heap this array we compare an array implementation of the heap. Yes, so someone is asking whether this tool is testing the difference between extracting the mean from an array, finding the mean and extracting it from an array, and finding the mean and extracting it on a heap. And this is an array-based heap, and this is the case, but this is the case simply because we are going to implement the binary heap on an array-based version of the binary heap. Okay, so our implementation of binary heap will be based on an array, but we will see it from the API. So let me move to the API of the binary heap, just to let you know what's going on. So if you go to include and you will see into the directory include, you will see a file called binary heap.h. This file will contain basically the API of our library. This is the API, and as you see here, I added many comments to the API. So the meaning of the parameters and the semantics of the function we are going to implement, it should be clear. Okay. So for instance, if I want to know what's going on with build heap, it's easy, but let's say delete heap, I simply have to read the comment above it. And the idea of so what's going on, what's the meaning of calling delete heap on a bin heap? Well, the meaning is I want to destroy the binary heap. Okay, this function releases the memory space required to represent a binary heap. Please notice that the array A, which stores the key on the heap, will not be free. So from here you can figure out that we are going to implement an array-based version of the binary heap. And for instance, it would be much more clear here if we see what's going on with the build heap function. Well, the build heap function simply build a new heap, and this function build a new heap and fill it by using the values in an array. Okay, so by looking at the meaning of the parameter, you can figure out what's going on. So A is an array used to store the key in the heap. So from here you can see that the binary heap we are going to implement will be an array-based version of the array binary heap. It is also used to pass to this function a set of value to initialize the heap. So let's say I want to store all the values contained in an array A in a new binary heap. Okay, so to do so I must pass A to this function. And the second parameter would be the number of elements in A to be used to initialize the heap at the beginning. So in this way we are able to provide an array which is much larger than the initial size of the heap, so we can grow it basically without the need of changing A, of course. And this is it. So let me see, someone new is asking something. When we try to comment, we get an error. Can you tell me what's the error we see make, please? Because I hadn't any error in my code. So tell me what's going on. Target in our runtime destination for install target in no runtime. Okay, I'll try to fix the code. Targets give no runtime destination for executable target. I see. That's weird because I have no problem with it. Let me see. Oh, I see the problem here. Can you try to remove this last part? So here you can see install target executable. Can you try to remove it and leave executables and see what's going on? So let me new terminal and make list. Oh, let me first remove the cache, recompile it. Okay, can you try to do it? Let me go on. I will try to fix your problem as soon as I figure out what's going on. If the problem still persists, please just comment out this instruction, so remove install. So remove install, or simply place hashtag in front of the 3-line beginning from install. Okay. And let me see whether this is enough. Apparently it is. Okay, let me know. However, going back to the bin heap, let's have a look to what we are going to do here. So as I said, A will be the array used to store the key of the heap. It also, so the value in the node of the key of the heap. It's also used to initialize the heap itself. And the number of elements, so the second parameter in the build heap implementation will store the number of elements used to initialize the binary heap at the very beginning of the computation. So we are passing an array, but not all the elements in the array will be included at the beginning inside the binary heap. And so to tell build heap how many elements in the array should be initially included in the heap, we have to pass a parameter, and this parameter is the num_m element parameter. Max size, oh yeah, okay, yeah, I'm missing something, and we will see why. Okay, so max size is the maximum number of nodes in the heap, which should basically correspond to the size of the array A. Okay, here we are missing something. Let me add it online. So here we are missing the key size parameter. And what's the meaning of the key size parameter? Well, since our implementation should be as general as it is possible, we don't want to say what's the type of the values stored inside our heap, inside our binary heap. So basically we don't want to say that the array A is an array of integer, we don't want to say that A is an array of floating point, and so on and so forward. So to be as much general as it is possible, we have to pass an array of void, meaning that is a pointer, but we don't know the type of the pointer. Okay, we don't know the type of the element stored into the array. So how can I of course, since the type of the element stored in the array correspond to the size in terms of bytes required by the elements in the array itself, to know where is stored the third element of the array, for instance, I need to know the size of the element itself, the elements themselves. So the first element of the array A will be stored, of course, in position 0 of the array. So in the is pointed by A itself. What's the address of the second element in A? Well, the address of the second element in A will be A plus the size of the elements in A expressed in bytes. Okay, and to know it, so to know the size of the element we are dealing with inside our okay, commenting the lines working. Okay, I will try to find out why you are having. Oh, by the way, for those who are facing the issues of CMake, can you send me an email saying I'm working on Windows, I'm working, just to figure out what's going on, because as you saw in my system, I'm not facing this very same problem, so everything works fine. So I would like to fix the problem and to understand what's going on. So please send me an email saying in which system you are working, what software are you using, and so on and so forward. If you can, of course. This is just to fix up the things on the repository. So as I was saying, to understand, to being able to handle the element in the array A, since we don't know what's the type of the elements in the array A, we need to know at least the size of the elements themselves in terms of byte. Okay, so for instance, if I'm working with if I'm working with a 64 bit system, the integer were represented as a number in 8 bytes. So, and if A is an array of integer, the second element of A will be placed in A, so the pointer A plus 8 bytes. Okay, and this is a way to know where to find the second element in the array A. Of course, what about the element in position 10? Well, the element in position 10 will be A plus 10 multiply key size. Okay. Okay, so what's this? Okay, this syntax, this is just a comment. Someone is asking what's the meaning of at parameter. As you can see, this is a comment, and I'm using a syntax for a tool named Doxygen. We are not going to see Doxygen, but since I want to be as much clear as I can, I use this syntax, which is quite standard, let's say. And this is a way to say that in our function there is a parameter, which is the first, second, third, fourth. So the fourth parameter of our function is called key size, and here I'm writing the meaning. So this is key size is the size of the type store of the type. Well, let me write in this way, is the type size of the values stored in A. Okay, so meaning is the size in byte of the value we want to store in our binary heap. And this way we are able to write a single function to deal with any possible type of values. Okay. Now, of course, since a binary heap depends on the total order, to be as much general as we can, we need to provide also this total order. So what's the total order? Is simply a binary relation amongst elements. Okay, so we have a set, and we have a total relation between this, the element of these sets. Since again we want to be as much general as possible, we have to provide this binary relation to our data set. In this way we are able to build by writing a single build heap function, we are able to build both being a min heap or max heap, or having any kind of binary heap you want to deal with. Okay, and this is done simply by passing as last parameter a function which is the total order we want to deal with. So if you wonder what's going on here, as you can see, the type of the last parameter, which as I said is a total order, is total order type, which is a type defined in the heap, in the header total order orders H. As you can see here, I'm simply defining the total order type as a function, a pointer to a function which takes two constant pointer to values. And please notice again, since we are dealing with unknown types, here we have a pointer to void, okay, and returning an integer values. Of course, since we are assuming that this is a total order function, let's say comparing A with B, the result of executing this function on two pointers will be 0, well, 1 whether A is smaller or equal to B with respect to the total order we are dealing with, or 0 otherwise. Here we have also okay, here we have also three different kind of total order. For instance, we have total order for floats, less or equal total order for floats, which is useful to build min heap of floats. Here we have an implementation of less or equal among integer, which is of course useful to build min heaps for integers. Here we have a greater or equal for integer, which can be used to build a max heap. And as you will see, we will use all these total order, which are I mean are not really special, but I decided to include them on the library because they are quite frequently used, let's say, at least. And you can see the implementation of this total order simply by looking at the totalorders.c file, and this is quite easy. So let's assume I'm calling the less or equal float relation on two pointers a and b. Well, since this is a less or equal function relation on two floats, of course this pointer should be typecast to floats, and this is the case. And then I must ask myself whether the element pointed by these two pointers satisfy this relation, which is the less or equal. So quite easy implementation for it. This is just a way to embed the less or equal relation inside a function. Okay, so you may wonder why haven't we simply used this relation inside our build heap function? Well, the point is that we want to stay as much general as we can. Okay, what does this notation do? So some of you were asking what's the meaning of this notation. Well, this notation is meant to say that this new type that I'm defining by use type def, okay, is basically a pointer to a function, okay, returning an int value and whose parameter having two parameters which are both constant void, pointer to constant void values. Okay, so instead of writing something like let me just mess up things, writing something which should be much more familiar. So instead of writing int new type, okay, I want to define a new type for functions. So to define a new type for pointer to function, I use this notation. Okay, and now I can this new type basically means that I can pass to. So going back to let me go back to the build heap function, and we will see in a while a call for it. So since I define total order type in this way, and I'm saying that total order type is basically a pointer to a function having two parameters which are constant void pointers and returning an int, I can use the new type as a type for a parameter. Okay, in this case, I think this is clear. So now let's assume we have written the build heap function. We can go to let me see. We can go to test insert, which is one of the tests we saw before. If you remember, I called test it certain point, test insert a certain point, and I was getting this stuff, and I tried to insert the number 3, and I end up with nothing simply because we are missing implementation. Well, this executable corresponds to this new function, to the piece of code you are seeing here. And as you can see here, I'm calling the build heap function we were seeing here. Okay, and the last parameter is in this case is one of the relation we saw on total orders. So here basically by writing things in this way, I'm saying I'm building a min heap of integers. Okay, and please have a look to this call of build heap, in which basically I'm doing almost the very same thing, but the last parameter, which is the relation we are using to specify the function, in this case the relation, the total order we are using is greater or equal to bit among integers. So while in this case we are building a min heap, by using this call we are building a max heap. Okay, so building min heap or max heap or whatever you want, it's much easier by using this kind of signature. Yes, total order, we need a pointer. So someone is saying, so to be a total order, we need a pointer to a function whose template satisfies definition of a type def, right, as we saw here. Okay. So since the getIn function, you can see it from the box, the greater or equal int function takes two constant void pointer and returns an integer. It is a total order, and so I can use this function as parameter of build heap. Okay, I think this is more or less clear. So this is what I want to say about the parameters. Let's have a look to the function we are required to implement to have a full implementation of the binary heap library. Well, first of all, we are missing the structure. We will see which structure is the best one here. We are missing the isHeap empty function to decide to establish whether an heap is empty or not. We are missing the min value of the heap. Okay, so I don't want to handle directly the elements in the heap. I simply want to call the min value function to get the minimum among the values stored in the binary heap, and this value will be returned as a pointer. Again, since we don't know that the real type stored in the heap at this level, so by writing this function in the moment in which we write this function, we still don't know the type of the value stored in the function in the heap itself. So we must return a pointer to that value, and of course this pointer will be a pointer to the initial element in the array which will store the values in the heap, and so to the root of the heap, of course. We need a function to extract the minimum, so we don't want of course we want to get the value, the minimum value on the heap, but we will also need to remove it from the heap, and we will see how to do it. And this is build heap function, what we saw before, which is used to build a new heap and allocate all the space required to perform to do it, with the exclusion of the array A, which is pre-allocated. And we will have also a delete heap. Of course, since I need to allocate an element, some space to have a binary heap, we need also a function to deallocate all this space to avoid memory leaks. And of course we will need a decrease key function, which will take the binary heap, a pointer to the node which will be which will contain the new value, and the value itself, which will be at the end of the computation stored inside the node, and this pointer will be a pointer to the final node in which the value will be stored. Okay, so remember, we are dealing with an array-based version of our binary heap. We must provide the position of the node we want to change. By changing the value, it could be the case that we broke the binary property, so we need to fix up the property, and by fixing up the property we change the position of the new value we inserted inside the key. So at the end of the process we may want to know where the new value has been placed, and so the decreased key must return a pointer to the new position of that value. Okay, and we of course have an insert value function which takes a binary heap and the value and build up a new node, and as I said before, insert a certain value inside the node, and which by looking at the slide we said that to insert a new value we have to build a new node and insert the infinity with respect to the total order we are deciding to use, and that value will then be decreased to the value we want to insert. However, this strategy, we will see, is not really the best way to do this stuff, simply because we need to know what's the largest possible value for the type we are dealing with, and this should be provided at some point inside the build heap function, which is quite unnatural. So we will try to figure out a different way to handle this process. And just to let you know, a good idea could be to build up a new node and insert instead of inserting the infinity with respect to the total order, just insert the maximum value among those which was inserted in H. Okay, so if during the computation at some point, for sure I will insert a set of elements inside H. If I want to insert a new element, just build a new node and label it by using the maximum among the values already stored inside the heap, and for sure that would be enough to preserve both the heap topology, and this is done by inserting the node in the position we mentioned at the beginning of the lesson, and will be enough also for the heap property, because since this is the new node will be labeled by using the maximum among the value already inserted in H. For sure there will be in H no element, wouldn't be in H any element greater than that value. Okay, and so of course its position would be correct from the heap property point of view, but we will see it. Okay, and finally we will also need a print heap function for just to see what's going on. This function will print on the standard output the heap, and of course, since we are dealing with values whose type is unknown, we need to pass to this function a function which print on the standard output these values. Okay, so whenever you want to print an integer, you need to provide a function which takes a pointer to an integer and print it. And we will see during the implementation what's going on, but just to give you an idea, going back to the test insert program, this is to print, to have in output an heap, we need to implement a function like this, which takes a pointer. This is a an int printer, sorry, simply because we are dealing with binary heaps of integer. This function takes a pointer, which is a pointer to an integer, and print in standard output it. Okay, why cannot we do it without this function? Well, simply because at the library level, so at this level, we don't know the types of elements stored in H. So we need a function to decide what to do with a value in H. Okay. Now, going back to the structure. So what's does we need here to implement this data structure? Well, for sure we need a pointer, void, a pointer to A. So remember, A, this is the array used to store heap values. Okay, well, heap nodes. Okay, and for sure we also need signed int the number of element of the heap. So at each moment of the computation, the number of element in the heap is the number stored in this member of the structure. So this is the number of nodes in the heap. Okay, and then we also need to know the maximum number of element in our heap, so the size of the array A basically, and this is max size. Okay, this is the maximum number of nodes. Let me write it, size of A. Okay, and of course, since already said before, we don't know the type of element stored in the heap. We need the size to handle all this element. We need the size of the type of these elements, and so let me call it key size. So this is the size of the key type. Okay, so the key are the values stored in the heap. Any question? Okay. So moreover, of course, since every binary heap is characterized by a total order, we need to specify this total order. This is done by adding a new member to this data structure, which is the total order itself, and we call it less or equal to, just to clarify what's going on. And this is the heap total order. Okay. finally, as said before, we need a furthermore member in this data structure, and this member will store the maximum value handled by the heap from its creation. And this will be done in inserting an element, a new value, sorry. So in inserting a new value, first of all, we will create a new node as saw during the slides, but instead of assigning infinity to that node, and please notice that infinity, we need to know the infinity with respect to the total order, and we don't know it. So instead of doing it, we will assign initially to that node the value, which is the maximum among the values handled by the binary heap. And to do it, of course, we need to know the maximum of the value handled by the binary heap from the beginning of the computation. And so we need a void, a pointer to a memory location, which will be able to store that value. Okay. Now the point is here is if we were trying to implement binary heap amongst integer values, then we may simply have written int here to store the maximum among that values. But since we don't know the value we are storing into our binary heap, we need to have a pointer to a memory location whose size will be, of course, equivalent to key size, and this will be used to store the maximum value of the order. Well, not the maximum value of the order, but the maximum value of the order that has been stored in the heap until now. Okay, so we don't care whether that value has been removed or not. We are only interested in the fact that that value at some point of the computation has been handled by the heap. Okay, so this is the maximum value stored in the heap. I mean, I want to stress this part. We don't know whether this value is already in the heap. Okay, it could be removed. Okay, but the real important thing is that for sure any value in the heap is smaller than it. Okay, and this is enough for us. So this is our binary heap data structure, and by using it we can start the implementation. Well, of course, to implement it we need to go into the binary heap C file, which already contains all the function, but unfortunately, as you can see, the function must be implemented. So let's start by defining some useful macros. So we may define what's a parent, okay. By the way, happy parent day if you are part, but I don't think so. However, okay, let's define the parent macro. So what's the parent macro? The parent macro will be, so if I have a node, I want to know, I know the index of the node I'm dealing with. I want to know what's the index of its parent. Well, the index of its parent will be, well, we saw on the slides that to get the index of the parent, we simply have to to divide by 2 the nodes. Okay, this is what we saw on the slides. But here, if you remember, on the slides we were dealing with indexes going from 1 up to n, and here we are dealing with the indexes going from 0 up to n minus 1. So to get the index of a given node, of a given index, the index of the parent of a given node, we have to first of all subtract 1 and then divide it by 2. Okay, so what's the parent of 1, which should be the left child of the root? Okay, so 1 is the index corresponding to the left child of the root. Its parent is 0. So if I to get it, I must subtract 1 and divide by 2. Okay, what's the parent of the right child of root? Root has index 0. The right parent of root has index 2. So to get the index of the parent of the right child of root, I must take 2, subtract 1 and divide by 2. Okay, of course this division is an integer division, so by dividing 1 by 2 I end up with 0, and there should be a reminder, of course, but we don't care about the reminder. So this is a way to get the index of the parent once we have the index of the node. Now let me define the left child of a node. So let's take as example 0. So 0 is the root, and it's not enough to multiply the node by 2, because 0 multiplied by 2 end up in 0 again, and of course this is not the left child of the root. The left child of the root is 1, so I need to first of all multiply by 2 the node and then sum up 1. Okay, and this is the left child. What about, again, this formula is different from the one we saw. Well, let me do this stuff to avoid any mess in the computation. So this formula is different from the one we saw on the slides, simply because on the slides we were dealing with an array whose indexes went from 1 to n. Here we are dealing with arrays whose indexes goes from 0 up to n minus 1. Okay, and what about the right child? Left and right. What about the right child of a node? Well, of course you can get it in this way. Okay, and this is a way to get the index of a given once you have the index of a given node, to get its parent, left child and right child. Of course we may need also a way to see whether a node is valid, and what I mean by valid node. Valid node H node. So a node is valid whenever the number of element in the heap we are dealing with is greater than the node itself. Okay, and again let me use as many parentheses as I can see here, just to avoid a mess once I'm using the macros. So what I mean by valid node, I mean that node is included into H, and a node to be included into H, an index of a node to be included into H should be smaller than the number of elements in the heap itself, simply because again we are dealing with indexes going from 0 upward. So if my heap contains 2 elements, the valid nodes will be 0 and 1. If my heap contain 7 elements, valid nodes goes from 0 up to 6. Okay, so a node is valid whenever it is smaller. Well, an index for a node is valid whenever it is smaller than the number of elements of the heap. And finally, for today, let me define other 2 macros, which will be quite useful, which is the address macro, which take an heap and an index for a node. So let's say 0, for instance, and returns the address of that, so a pointer to that node inside my data structure. So since all the values will be stored in A, okay, so this node will be an index for A, and then the address of the node in H will be A, so HA plus node multiply by what? Multiply by the size of the value I'm dealing with. So here I must use key size, and this will be the address of the value stored in the node. Okay, well, not the value, but a pointer to the value stored in the node. Okay, so this is the base for the address, and this is basically as saying I'm skipping all the nodes coming before, which each of them have key size, and so since I'm looking at the node, I simply add to the base of the address this value and end up with the position of the value I want to deal with. And of course I need also I will need also the reverse macros with respect to this one, which will be index of. So these macros will take an heap, an address, and will return the index of that address. So that address will be an address of the node, and we'll get, and by using this macro I will able to compute the index of the node, so the name of the node whose key is stored in that address. Okay, so that would be address minus hi. So let me do in this way just to avoid any messy things. And again here. Okay, so I'm subtracting to address hi. I get a certain amount of memory, and that memory will be the memory required to store all the nodes that comes before the nodes I want to deal with. So I can simply take that value and divide it by key size, and by doing so I end up with the index of the node whose values is stored in the address. Okay, this is it. And I think this is more or less all I want to show you today. Tomorrow we will see the implementation of the functions, so of the API of binary heap. which well, not tomorrow but the next lesson, sorry. Of course, as you may have figured out, the toughest part is already done. Basically, here we basically need to implement all we saw on the slides in the previous lesson, and it would be, let's say, more or less easy, but we will see it next time. So if you have any question about what we saw today, please don't worry, send me an email. I'll try to reply during the next lesson on Monday, and this is all basically. Okay, and as I said, please tell me, try to send me an email saying what's the system you are using for those who had the problem with CMake, and I'll try to fix up all the things for you for the next time. Okay, thank you so much, and see you on Monday then. Hopefully. Bye.